All right. Welcome back again. So today we're going to start our lecture on shared memory programming. Especially, we're going to talk about Pthreads, C++ standard thread library, and finally OpenMP, which is the one of the most important topics in this class. First of all, have a short review of a shared memory system. So can anyone tell me what a shared memory system is and why it is useful? But that's your very first question in this lecture.
When we have more than one processing unit and they want to coordinate some data exchange, let's say, we can have a memory that all of them can access.
Yeah. So in a shared memory system, the entire memory, as we can see here, let me see. The entire memory is shared among all CPU cores or all CPU threads, right? So, so you can see the diagram here. We have different CPU cores, these ones, and they are somewhat connected to a global memory address. So all of these CPU cores have access to this global memory space. And this can be quite helpful in some applications. For example, shared memory can help us to coordinate the work of the cores. And for example, they provide a global memory provides implicit communication. So for example, this core, in this case, can write something into the memory, and another core, probably this one, is waiting for something to be written in that memory block. So consider we are talking about this block. So this core is writing something here, and this core is waiting for the data in this memory block, right? So this way, this core and the second core, this one, they can have some sort of implicit communication through this memory block, right? So in this case, you don't need to have explicit communication using message passing, for example, that you do between processes. So this is something that shared memory provides for us, and using this shared memory, different cores can have collaboration, so they can collaborate on solving a problem together, right? So, so these are one of the most basic features that a shared memory system provides for us. And when you're talking about shared memory, we are talking about uh, general computers like laptops and desktop computers. So for those computers, we can have two programming strategies for these shared memory systems: multi-threading and multi-processing strategies. Both strategies are used in parallel and concurrent programming, but there are somewhat different paradigms. So now the question is, what is multi-threading and what is multiprocessing, and what are the difference between these two concurrent programming or parallel programming paradigms? This should sound familiar from your operating system class if you had it before. So anyone can tell me what's the difference between multi-threading and multiprocessing?
I think you explained about it in the first session that one of them is using multiple CPUs, and the other one uses timing of the processes to give us the impression of parallelism.
Yeah, well, this is the difference between concurrency and parallelism, right? With multi-threading and multi-processing, you can do both. You can do concurrency, concurrent programming, and you can do parallel programming. But using multi-threading and multi-processing, you do it kind of differently. What about any other answer? All right, so probably we should talk a little bit about the concept of a thread and a process. And then it will be clear what's the difference between the two paradigms. Okay. So now it comes to the next question. What is a process in an operating system or a computer system? I wrote it here, but this is very abstract. So can anyone tell me that?
I think a process can have more than one thread. It's like many threads are
Okay,
trying to
but
achieve
we
one
haven't talked
bigger
about
goal.
threads, right? We are just talking about
Okay.
the process. So conceptually, what is a process in a computer system?
It's an entity which is trying to achieve something, and it will have its own resources unit,
Yes,
like memory units, and right?
yes. That's a rough definition. So a process is an instance of a running program, right? So if you develop a program and if you want to run that program, who runs that program for you? It's the operating system, right? So the operating system creates a process, which is a conceptual model, creates a process that process is responsible for managing your program. So a process can have some memory address, file descriptors, and access to resources and everything, right? So this is an instance of a running process, and the processes, which are instances of different running programs, they are independent to each other. So they are kind of independent and they don't have access to each other resources, including memory and like file descriptors and so on, right? So this is a very rough and basic definition of the process. If you are not familiar with that concept, I strongly recommend you to study processes from one of the operating system books that I introduced in the class. All right. So with the process, then we can define a thread or a thread of control. So a thread of control, as I defined here, is independent sequence of instructions within a program that can execute concurrently, and they share the same resources of the process. So basically, a process is an instance of a running program, but inside that process, you can have different threads of controls, different independent sequence of instructions that can be executed concurrently. And by concurrently, I mean one instruction can be executed at one time, and another one can be executed in another time, like these interleaving things. That's why threads are also called lightweight processes. So if you look at this the diagram in the right, here we have a single-threaded process, and in the right we have a multi-threaded process. So single-threaded process has like a code in it. So this is a process, our process, has code segment, data segment, some file descriptors, a set of registers for managing the program execution, a program counter, and a stack memory, right, that we talked about before. And then this process has a single thread of execution, which means that it can only execute one sequence of instructions. So with this definition, we can have multiple processes or multiple single-threaded processes, right? So this is about the process and a thread in a process, but in a multi-threaded process, you still have some shared resources like code segment, data segment, files, and also the memory space that is allocated for that process. But you can have different thread of control, right? In this case, we have 3 threads of control. And each thread has its own set of registers, has its own stack memory, and has its own program counter. So, which means we can independently execute 3 sets of instructions, right? So the question now is how many threads we can build as a programmer for a process. So how many threads we can create in a process? Can someone tell me that?
I think it depends on both the OS and the hardware.
Okay, but from programmer's perspective, is there any limitation on a number
No,
of threads that we can create? Okay, no. But what about hardware perspective? How many
Um,
threads can we create?
it depends on what kind of threads they are, how much
Yeah, if
like
you remember,
calculations.
yes, if you remember for a diagram of a CPU, we had different units, right? Fetch decode unit and ALU, and we had something called execution context, right? Which was contained by a set of registers, as I explained before. So each thread lives in a execution context. So if a CPU core has, for example, two execution contexts, so from hardware perspective, you can create two threads, right? So that's why it's important when you write parallel code to know the exact number of hardware threads, these execution contexts, right? Then you will know how many threads you should create to have the true parallelism, right? But if you create more threads than the execution context that you have available, what part in the system is responsible to allocate these threads to this execution context? So who manages these this switching between threads on the hardware?
Schedulers and dispatcher, I would say.
What's the bigger picture? So what's that piece of software that does this thread
Oh,
management for
the
us?
OS.
Yes, so that's the operating system. So from programmer's perspective, programming point of view, you can create different threads, right? And it's up to the operating system to manage these threads. But keep in mind, switching between threads, or which is technically called context switching is kind of it's not a cheap process, so it's expensive. So you should have some sort of control over your threads. Okay, so enough about threads. You have already studied that from operating system class. So as you mentioned, also a single process, sorry, a single process may have multiple threads of control, right? So now that you know the definition of a process and a thread, so what is multiprocessing if thinking about a parallel piece of software? And what is multi-threading? So what's the difference between the two? It should be a little bit clearer now.
Multi-threading when we want to manage many threads running on the hardware, first from the hardware perspective,
Well,
simultaneously.
it's about programming strategies, right? So let me explain a little bit about this too. Multi-threading refers to the programs that you create multiple threads within a process, right? To perform some certain task, to do some sort of computation, right? But in multiprocessing, instead of creating different threads, you are creating different processes, and those processes may have only one thread inside them, right? So this is the basic definition of multi-threading and multiprocessing, but there are some differences. So from, for example, memory perspective, in multi-threading programming, which you have multiple threads to perform some parallel computation, the threads, they share the memory, right? So different threads, all of the threads that are in your process, they have access to the same memory space, correct? But that's not the case in the process because the processes are isolated. So even in a shared memory system, if you do multi-threading, you have a shared memory space from software perspective, but in a multiprocessing, your memory is isolated. So if two CPU cores in a multiprocessing programming want to communicate to each other, they have to communicate explicitly using a message passing mechanism through sockets, for example, right? But when you have multi-threading, because the memory space of a process that includes that contain these threads, because that memory space is shared, so the threads can communicate to each other through the memory, not through explicit communication. So in that case, the communication in multi-threading programs are cheaper than the communication in multi-process program, right? So now someone tells me that which one has higher overhead? Is creating a thread is more difficult than creating a process, or they have the same complexity?
Multi-threaded processor is more difficult when you have more than one process, I mean.
Yes, because creating a process is more complex than creating a thread, because you need to create more things. You need to create a memory space for each process. You need to have a code segment, data segment, and everything, right? But in a multi-threaded program, you create one process, and within that process, you create different threads of control. And these threads of control, they can share the memory and other resources of a process. So it has lower overhead. So it's kind of cheaper to create different threads than different processes, right? So what about the performance? Which one is typically which one has a faster context switch? So if the operating system wants to change from one thread to another, is it cheaper to use threads, or it is cheaper to switch between different processes rather than the threads? So what about that?
Yeah, threads are cheaper because they share the
Yes,
memory by default.
yes, of course. So this was quite obvious. What about race condition? Which one is more prone to race condition? Multi-threaded program or multi-process program?
I think both of them need handling, but multi-processes will be more difficult to handle.
Well, in multiprocessing, because the memory space is isolated, so it's less prone to data race, right? Because the processes, they don't have access to each other's data. But when you talk about multi-threaded code, because the resource, especially the memory, is shared among all threads, right? So data race can happen. So in multi-threaded program is more prone to data race. All right. And there are also other differences, but in this course, at least in the shared memory programming part of the class, we mostly talk about multi-threaded programming. But when it comes to distributed computing architecture, what we do is multi-processing programming, right? Okay. All right. Any questions so far? Okay. All right. So there are a lot of ways to write shared memory programs, to write multi-threaded programs. Essentially, in this course, we talk a little bit about Pthreads, which is one way of doing multi-threaded programs. And then we talk a little bit about a standard C++, a standard thread library, which was introduced into C++11. And then we switch to OpenMP, which will be the main focus on this course. And this is and it's one of the widely used parallel computing libraries or specifications for shared memory systems on CPUs, by the way, not on GPUs. So OpenMP only supports CPU computing, right? So you have this multi-core system on the CPU chip, not on GPU. All right. So first, I'm going to talk a little bit about Pthreads or POSIX threads. This also should sound kind of familiar from an operating system course if you had, but let's talk about it. So how we can write a parallel program. So I'm very specific with this sentence. How we can write a parallel program for a shared memory system using POSIX threads. So that's exactly what we want to do. All right. So first, let's see what this POSIX actually mean. So anyone knows that? Anyone knows what POSIX is actually?
Yeah,
So please.
like what it describes, it's a Unix-based OS library. It helps working with like multi-process and multi-threadings.
Well, it's not a library, it's a set of APIs and specifications,
Yeah.
right? Because in the beginning of Unix systems, so you could have different Unix versions, and those Unix versions, they had different APIs, for example, for system calls, creating threads, memory management, and things like that. And this POSIX, which stands for Portable Operating System Interface, was an API that was designed and introduced, I think, by IEEE to ensure compatibility between different Unix-like operating systems, right? One of the implementation and one of the APIs that this POSIX interface provides is POSIX Threads or Pthread, which is a POSIX version of the threading library that you could have on your operating system, right? So based on the definition of this POSIX threads, you should immediately know that you cannot really use Pthreads or POSIX threads on Windows machines, right? Because Windows is not a Unix-based operating system. So these POSIX threads are only available on Mac and also on Linux operating systems, right? Okay. All right, so this Pthreads library, which is included in POSIX API, provides system calls for create and synchronize threads. So synchronization is something that we talk a little bit about today. And it is not completely, but relatively uniform across all Unix-like operating systems, right? Okay. So it's a library that is included in your operating system in Linux and Mac to work with threads, to create threads and synchronize them and so on. That you're going to see some of those today. And it also support parallelism, so you can write parallel code and also asynchronous code using this Pthread library. You can synchronize your code. You can by synchronization, you can, for example, avoid that data race problem. However, because it is designed for shared memory programming, it does not really support explicit communication because you have a shared memory and you can use pointers to communicate different threads, right? Okay. So let's see how we can create a thread using this POSIX interface. So the main function that you should use for creating threads is this pthread create, which is available in pthread header file. So, but I will show you later. But anyway, so with this pthread create, you should provide some arguments. The first argument is the thread ID. So you should create a pthread struct in C, and then you pass its address to this function. Then you have thread attributes. Usually you use null in this case for default, but if you want to have different stack size, or if you want to provide priority, you should create this attribute here using this structure or struct. And finally, not finally, but the next one is this complicated thing, which is called function pointer in C, which is a pointer to a function, right? And this function should have a pointer to void, pointer to anything as an input argument, and as an output argument, it also has a pointer to void and point to any structure, data structure, right? Oh, sorry. And finally, you pass in the arguments of that function. So it's kind of abstract in the beginning, but let's see an example to see how it works. So this is the signature of this pthread create, and this is how you call it. So you have a pthread create. You pass in the address of the thread that you created with this pthread structure. Then as a default, you can use null because you don't have a specific options for your thread. Then you have your thread function, which is the function that is executed by this thread. And finally, you can have your arguments, right? And this pthread create returns 0 if the thread creation process was successful, and it returns a non-zero error code on failure. So you should always check if this pthread create was successful. Okay, so let's see a hello world example using this POSIX thread. So I haven't written it here, but you should include pthread header. So let me see if I can write text here. I don't think so. What about here? Yes, I can write here. So you should include in your C program pthread right here, right? And then you can use its functions. So the first thing that you should do when you want to create a thread is to create a function pointer, right? A function that gets void star, like a pointer to anything, as an input, and it returns a void star type. So for example, here we want to say hello. So my function name is say hello. It gets void star and it returns void star, right? And then I do what I want to do in this function. In this case, we simply print hello world, and we return nothing, right? So in this case, so this was my function to be run on each thread, right? Then in the next step, which is in my main program, I have to create threads and then execute them, right? So in this case, here, I am creating an array of 16 pthreads called threads, right? So this is a C array, right? And then I will, in a for loop, I create threads. So this pthread create, right? So in this case, I just need to provide the address of the thread that I created right here, right? So this is the address of the thread that I created in the for loop. So with this tn thread number index. So I use default setups for the thread, and then I pass in the name of this function that I created here, right? And finally, because this function receives nothing, so I just set null to indicate that I don't have any input argument. So as this for loop iterates, you create a thread, and immediately after your thread is created, this function runs in your thread. So in this case, the first thread is created, and then that first thread runs this function. Then the next thread is created, and that thread runs this function again. And these things by default are done concurrently, right? So if you have created, if the number of threads that you have created matches the number of threads on your hardware, depending still on the operating system, all threads may execute at the same time, right? Okay, so in this case, we have this parallelism so far. So finally, we have to use this pthread join to join all threads. So before I explain that, anyone knows what this join operation here, what does it do when you call this pthread join?
I think simply it will initiate the threads to start running.
I didn't get your answer exactly.
Yeah, like when we call it, they will start running.
Yeah, but the threads are running when you create them here. But here, you join them, and what exactly this join mean? It should also familiar from the operating system. Yes. So yeah, the answer is in the chat. So it blocks the main thread, right, until the threads are completed. So that's correct. So what does this main thread mean? So when you are working, when you write a program without any threading thing, you at least have one thread, right? So that one thread that executes your program, which is, you can see it as a single threaded process, that one thread is running, right? So here, the main thread creates this array. So the default thread, the main thread or the master thread. And then that main thread creates these threads, right? And then they execute. And finally, if I don't have this line, if this piece of code, my main thread returns, and we are not sure if other threads that we created are still executing or the execution is done. So when you write this pthread, when you call this pthread join, you are telling the main thread to wait until this particular thread, in this case, the execution of this particular thread is finished. So the main thread waits here, like in this part, until all other threads that you have created so far finish their execution. It is like to have an infinite loop here, and then you exit the loop after the threads finish execution. So this is why we use this pthread join. So from parallelism point of view, we call it fork join parallelism. Here you are forking the threads. I will talk about that in the middle of the lecture. And here you join the threads. So here you're forking, you are spawning threads, and here you are joining the threads to the main thread, right? That's why it's called join. All right, so this is a very simple hello world, parallel or concurrent program using pthreads, but let's see how we compile that. So here I am compiling it using GCC compiler, which works on Mac and Linux. So the compilation process is similar to our default compilation that we had before. So you provide the source code, you specify the name of your executable, but here you should also use this -pthread, which tells the compiler that we want to use this pthread library. Okay. You can also compile it with CMake that I think told you about last week, but I leave it to you to study how you can build pthread application using CMake. But you can see the configuration file in the slide. Okay. All right, so that was simply how you can let me delete this. Okay, that was simply how you can create a thread using pthread and how you can give a thread a task to execute. So now let's talk about the problem of data race in a multi-threaded environment and how can we handle this problem in pthread library. So I think we talked a little bit about data race before, and this also should be familiar from operating system because that's where this problem appears a lot. But let's talk briefly about that. So consider this code snippet here. Assume we have a global variable, in this case counter, right? And we have this function that is executed by each thread, right? Similar to that hello function that we had before. But in this function, we want to increment this counter variable. So we want each thread to increment this counter variable this amount of time, right? 100,000 times, right? So this is exactly what we want to do. So this counter variable is shared among all threads, right? Because we defined it as a global variable. So here, so it's not declared in the function scope. It's declared in the global environment of our code, and we call it a critical section. So a critical section is a section that different threads can have access to, and they can write on that section. And here I create two threads, T1 and T2, using this pthread create, and I call join, right? Okay, so if I run this code sequentially, which means if I call this increment function 2 times, what would be the expected result in this case? So what would be the final value of counter in this case? Can anyone tell me that? 200,000. Yes, right? So because we run it 100,000 and then we call this function again and we run it 100,000 more, right? Okay, so let me see if I have this implementation here. Okay, so let me share my my VS Code now. Okay, can you see my VS Code window? Yes, or
Yes.
okay. So this is the same code that I showed you using this counter. I tried to add a lot of comments, so you can read it if you want to later, of course. Let me zoom in a little bit. So here I have this counter variable, right? And then I run this program for 100,000 iterations. So and with 2 threads, right? So I have 2 threads, 100,000 iterations, and I want to have this counter variable to be increment, right? So here, instead of only 2 threads, I'm creating the num threads. The number of threads is this num threads, right? Okay, so and then I have this join, and finally I compute this expected value that I expected my program to generate, and then the real value of the counter. So let me compile this code. And let's see how it works. I have a problem with the terminal still. So gcc-pthread unsafe is the name. So I compiled the code. Let me execute it. So you see, when I run it, the expected value is 200,000, but what I got is this number, which has a huge difference, right? When I run it again, I get another one, another number. So the behavior of the system in this scenario, as you can see, is undeterministic. So I get very different results after each execution of the program. So the program of this type are called thread unsafe or not thread safe. So can someone tell me, let's first get back to the slides. What can someone tell me what exactly is happening here and why this problem occurs? Let me share the slides again. Okay. So why in this very simple program, so this is the simplest multi-threaded program that you can write, why in this very simple scenario, my expected result is different than the actual result? What's happening in this block of code? Any ideas?
More than one thread at a point will just read the same value and increment it equally, and then it wouldn't be like accumulatedly added to the
Yes.
counter.
Yeah, that's relatively true. So as you can see here, the problem starts with this counter variable in this critical section, right? The issue is this operation counter plus plus, this operation is not so-called atomic, right? So how many instruction is used for this operation to be performed? How many CPU operation we have here for
I
this
think 3.
counter? Yes. So that's how exactly, this is the assembly code, right? For this critical section. So each thread performs 3 operations. They first read the value of the counter variable into the register, right? They increment it by 1, and then they write it back to the register, right? So, but depending on the context switch and the operating system, they do it in different times, right? So for example, the thread 1 read the value in this at this point. This is time. These arrows are time. Change the value, and in some other time writes the value, right? But in between, another thread can read the value, change it, and write it, right? So what happens in this case, for example, is assume the value of the counter is 42, right? Then thread 1 loads 42, so it reads 42, and then thread 2 also reads 42, right? Thread 1 increments it to 43 and it stores 43, but thread 2 still has access to 42 because it doesn't have access to the register of another thread, right? So it's still 42, and instead of 44, your result is 43. And when you have a lot of iterations, this can happen thousands of times. So that's why instead of 200,000, you have a much smaller function, but much smaller value, right? So that's because you have this critical section, and this data is shared among threads, and more importantly, the threads can write in this section. If both threads only read this value, there wouldn't be a problem. But because at least one of them is writing, that's the issue. So data race happens when you have 2 processors or 2 threads accessing the same variable, and at least one of them is writing, and the access are concurrent. So they can access the same data in the memory simultaneously. So this is a very big problem in multi-threaded programming, and you should really be careful about data race. You saw that in a very simple scenario like this, a very difficult to catch bug can happen. So now assume in real world system how this data race can make your code very complicated. Okay. All right. So let's see how we can kind of solve this problem with synchronization. So synchronizations are some building blocks introduced in operating systems and managed by the operating systems to handle this data race. And you can see synchronization methods under the umbrella of something called mutexes, right? And a mutex stands for mutual exclusion or locks in some scenarios. You have different synchronization strategies like locks, and you can have different kind of locks like spin locks and so on. And you have semaphores and some other things. So the synchronization that we are going to talk in this class is one of the most basic ones, which is called mutex locks. All right. So before I explain that, can someone tell me what a mutex lock is and how it works?
Threads cannot access one locked variable simultaneously, and it has to be signaled so they can access that variable.
Yes. So how this mutex lock works is the following. So you first need to specify a lock. So you declare and initialize a lock, and then you try to your thread that is entering the critical section, like this section where you have shared variable, acquires the lock, right? Do the computations, and then it releases the lock when it is exiting the critical section, right? So your thread, in this case, we have two threads. They acquire the lock. So for example, thread 1, and do the computation and then release the lock, right? The important note here is while one of the threads has the lock, the other threads cannot enter the critical section and they have to wait. And this waiting process is managed by the operating system, right? So you have two threads. The thread 1 acquires the lock that you initialized before. So this is, by the way, this is not pthread syntax. It's just some pseudocode similar to C. So you create a lock. The thread that is entering the critical section acquires the lock, does the computation, and release the lock. And other threads need to wait until this thread done with the computation, and then another thread will acquire the lock. And everything is managed by the operating system. But you, as a programmer, need to identify the critical section and have these locks and write these locks properly. Okay. So this was very basic implementation of locks, sorry. But in Java and C++, you have some special locks called lexically scope synchronization, which means the boundary of the synchronization, the lock acquire and release, the boundaries are tied to the code block structure, which means that if you enter a code block, you are acquiring the lock automatically, and then when you're exiting your code block, you are releasing the lock automatically. But in Pthreads, you have to do this synchronization manually. So for example, here are two examples in Java. So this is in the object-oriented way, and this is the functional way. So for example, in the object-oriented way, you have a counter. So this is the global variable that you define in this class, and then you use this synchronize keyword. So each thread that enters this block here, this block, acquires the lock, performs this computation, and then releases it, right? And the similar thing happens in this syntax. In modern C++, without using this pthread library, but using a standard library, you can do something similar. You create a mutex lock, right? And then you define this lock guard using the mutex. And after you are leaving this block, the lock is released automatically. So this is some sort of this RAII idiom in C++ that is about like managing the resources within the scope of your class or your function. Okay. But when you're using Pthreads, you have to acquire the lock manually, and then you have to release it manually. Okay. Something similar to like memory allocation and similar things. Okay. So let's see how we can solve this problem. So as I mentioned, we have to initialize your lock, mutex lock. So you can do it with this pthread mutex underline T. Here you are just declaring your lock. And here in the critical section, you want to protect it using the locks. So before this counter plus plus, you have this pthread mutex lock, and then you pass in the address of this lock that you define. And then you have this pthread mutex unlock. So in this case, you are releasing the lock. Okay, so this is done manually. So you have to identify the critical section and try to have critical sections if you have to. Try to make them as small as possible. Otherwise, your code is sequential code. Okay? And in your main program, you initialize your lock that you defined here, right? And then you create your threads and you join, and finally you destroy the lock. So quite simple. So this is the three main steps. You initialize your lock, You declare actually, then you initialize it here. Then you protect your critical section. Finally, you deallocate or you destroy your lock, like to clean things up. So now let me show you the thread safe version of the same code that I showed you. Okay, so this was the unsafe version. Now I'm going to compile this thread safe version, which is a little bit different than the one that you saw, but let me have 2 threads only. So I have this mutex initialization. Then within my critical section, I have this pthread mutex lock. Then I did my computation and then I release the lock, right? So let me compile the code. Dash pthread, thread safe. Let's see. So when I run this thread safe, then the expected value and the final value are identical. And if I run it multiple times, I always get the same value, right? So it's important to synchronize your threads to avoid data race. All right, so let's get back to the slides again. Okay. Now I give you a scenario. Usually you can create multiple locks or multiple mutex locks, right? So in this scenario, for example, assume thread 1 locks A and then locks B, and thread 2 locks B and then locks A. So what's the situation here? What is happening here? I just accidentally showed you the answer, which is deadlock, right? So in this case, thread 1 is waiting for thread 2, and thread 2 is waiting for thread 1 to release the lock. So make sure that when you're defining these mutex locks, you don't get into deadlocks. But usually it's easy to avoid deadlocks, but you should be careful in your programs. Okay. All right, so I think that was enough for pthread. So now let's talk shortly about C++11 standard thread library. So let's see what is this std thread. So well, std thread or standard threads were introduced in C++11, and it is a standard thread library for C++. So it's portable, which means that it's operating system agnostic, and you can use it using Linux operating systems or Microsoft Windows operating system. So you can use this standard C++ library in basically any operating system that you have compiler for. But you have to make sure that you are using C++11. So when you compile your code, don't forget to use this --std equals C++11, okay? And it provides a high-level interface for multi-threading. It is using that RAI thing that I talked about. And it's also compatible with C++ standard algorithms. And finally, it has a cleaner syntax, and it provides better error handling. So it's a little bit easier to work with compared to pthread. So let's see how we can use it. So I will go through it quite faster because the concepts are the same compared to pthreads, but the syntax is kind of a little bit different. So it's a C++ code. You need to include IO stream if you want to print something to the screen, and then this thread header for this std threads, right? Similar to pthreads, we create a function, but here you don't need to have this void star and void star. So it's a normal C function, C++ function. Here you can declare the threads. So here we are creating an array of threads containing 16 threads of this std thread type. So this is the main type that you should use. And then instead of having that create a pthread create function, you just call the constructor of this thread type and then pass in the name of the function that you want this thread execute, right? And finally, you have this join operation. So quite simpler than pthread library, right? Okay. And for compilation, you should use C++ compiler. So GCC does not work in this case. You should use this G++. And then you should specify the standard, the C++ version using this -std C++11 or more. Then you should specify also this pthread, but it's not mandatory, so you can compile your code even without it, but it's good to use it because under the hood, this threads library on Mac and Linux use this pthread, and then you provide your source code, and finally your executable. So this is how you compile it. And if you use CMake, you can also use this configuration file to build your program. So quite similar. Similar to Pthreads, you can also have mutex locks here. So this is the same problem that we had before. So here I have this mutex thing, mutex declaration using std mutex. But before that, you need to include mutex header, right? And then you create this lock guard variable using your mutex, right? So in this case, after this line of code, you acquiring the lock, right? So here you have this synchronization, but after leaving this block, so you release the lock, right? So it's kind of automatic, and you have a scoped locking in this case, and then you can create your threads and then join them. Okay, so it's up to you with which library you want to work. Okay, so let's have a short summary of multi-threaded programming using Pthread and C++ standard library. So they are available in different programming languages. Using threaded libraries, you have fine-grained control over threads. You exactly know when you want to create your threads, how you want to manage your threads, and which thread is responsible for performing what task. So it's up to you how to control the threads, and you have a good level of control. You can use multi-threaded programming using these libraries to implement asynchronous and event-driven programs. So it is kind of flexible in what kind of multi-threaded program you want to write, and you can find popular applications of these libraries in web servers, GUI applications, file system, and even operating system themselves, message queues, and so on. But there are some limitations. Well, the first limitation is even though creating threads are cheaper than creating processes, still you have some overhead, especially when you want to have context switch. And if you are a naive programmer and you create thousands of threads, your program might stuck and you run out of system resources. So it's kind of difficult to manage this overhead in threads. Another problem is the data race. So there are in real world applications, it's quite hard to detect the data races. So that should be done really carefully. And you also have deadlocks. But more importantly, when you use general thread libraries, it's kind of hard to parallelize for loops, which are quite popular in scientific applications and data science. So we want a library, at least for the purpose of this class, to make us to enable us performing heavy computations, but without these limitations. So we don't really want to be worried too much about these limitations. And that library is available, and its name is OpenMP. So OpenMP, which is a widely used library for performing scientific simulations in parallel, image and signal processing, matrix computations, machine learning, and similar problems. So from now on, we're going to talk about OpenMP, and you're going to see how easily OpenMP can be used for performing scientific computations in parallel. But if you want to develop, for example, web servers, GUI applications, some software-oriented things, not necessarily numerical applications, I would recommend you to use this C++ standard thread library, or thread libraries available in other languages like Java or Python. Okay, so let's see what OpenMP is and how we can use it. All right. Well, by the way, is there any student who has heard anything about OpenMP, or it's completely a new topic for you? Okay, but about others?
I just heard about it, but never used it.
Okay. So I assume it's kind of new for most of the class. Okay. So OpenMP stands for Open Specification for Multiprocessing. So this is the meaning of the acronym, right? And as the acronym, as the definition, as it's clear in the definition, you can see it's a specification. So it's a set of tools and APIs, which means it has different implementations, right? So OpenMP is a standard. It provides a specification and APIs for parallel applications, especially in numerical computing, but you can find different implementation depending on your compiler and your operating system. So this is their website. You can see the community, their talks, tutorials, and so on. So you can have a look at their website as well. And as I mentioned, it's a high-level API for parallel programming, and it is mainly used in C, C++, and Fortran. In this course, we are worried about C and C++ version, and we don't talk about the Fortran version. But if you want to, you can find resources in this website. But OpenMP is not like a normal library in C. So basically, 80% of your OpenMP program contains preprocessors or compiler directives, which you define by this hash symbol, right? So when you use OpenMP, you tell the compiler what kind of parallelism is in your program, and you guide the compiler to make your code parallel during the compilation process using these compiler directives. And all of them in OpenMP starts with pragma OpenMP, and then you have some OpenMP specific constructs, right? So 80% of your code is these preprocessors, which makes OpenMP quite interesting because things are done by the compiler. You just guide the compiler how to do those things, right? And about 90% of your OpenMP program contains library calls. Library calls, for performing these library calls, you have to include this OpenMP header. And library calls are like when you want to set the number of threads or how many threads you have, get thread ID, and so on. You will We will see about them. And about 1%, you define environment variables to control and to have different configurations for your OpenMP program. But the main thing is to have these preprocessors or compiler directives. So these are important to understand. Okay. So let's see what OpenMP is from programmer's perspective. So OpenMP, apart from this API and specification, has some more features. It's portable, which means that it works across different operating system and compilers. It is threaded, which means under the hood internally, OpenMP uses POSIX threads, right? But you as a programmer are not responsible to manage the threads and thread creation and join operation and everything. So it's up to OpenMP runtime environment to manage that. It is designed for shared memory programming, which means threads have access to the same memory space. So it's for shared memory and multi-threaded programming. And it abstracts away a lot of complexities of working with these thread libraries like Pthread. And it provides a very neat syntax for you to parallelize your code, especially when you have when you want to parallelize your for loops. Okay, and let's see what actually OpenMP does and what it have and what OpenMP doesn't provide. So the first thing that it provides is to allow programmers to separate a program into serial region and parallel regions. So this is very important because it allows you to gradually parallelize your code, which means you can start with a serial program and you make that serial program a step by step, make it parallel a step by step using OpenMP. So we're going to have an example next week to show you how exactly you can make a serial program, a parallel program using OpenMP. So the serial regions in your program, they run by a single thread, and the parallel region, they run by a thread team or a team of threads, right? Okay, OpenMP, we also hide the stack management, which means as a programmer, you don't see how the complexities of the thread creation, stack size, thread local storage, and everything is done by OpenMP runtime behind the scenes. So you are not you don't need to worry about these complications. And it also provides some synchronization constructs to avoid data races. It does not avoid data race by default, but it gives you some good tools to to prevent data races. And let's see what OpenMP will not provide for us. So it does not parallelize our code automatically. So you as a programmer must explicitly tell the compiler how to parallelize your code, right? But with less complications. So it's not something that you get parallelism for free. You should, as a programmer, still know how you want to decompose your problem. It does not guarantee a speed up. So it means that you as a programmer have to use OpenMP efficiently because you are still under the hood have this synchronization for locks, for example, and thread creation overhead. So it's up to the programmer how to use OpenMP efficiently. And it does not avoid data races automatically. Still, although it gives you tools to avoid data races, but it's up to you to detect your critical sections and synchronize them. Okay. So in this table, I provided a list of useful and the most popular OpenMP directives. In today's lecture and the next one, which we don't have a lot of time, I'm going to go through most of them, but let me explain some important ones. So the most basic one is this Pragma OMP parallel, which which is used to create a parallel region, and that parallel region is executed by a team of threads, right? So this is the most basic OpenMP directive, pragma, OMP parallel, and then you start to have these curly braces, and within these curly braces, everything is done and in parallel. So here you have your threads running only in this region, right? If you want to get the ID of a thread, you should use this function. If you want to know the number of threads within this parallel region, you should use OMP get num threads. You can check the execution time by this OMP get wall time to get the wall collect time. Using this environment variable, you can specify the number of threads. You have this barrier and critical constructs. Barrier is used when you want all your threads to wait for others to reach that point, that barrier point. So for example, you have a barrier here and these are your threads. So all of them need to wait in this specific point until everybody is ready here, and then they can continue execution. You have this critical by OpenMP, this critical clause that it gives you, it helps you to avoid data race. So you can specify that this specific block, like using these curly braces, this is a critical section. And in this case, only one thread can enter the section, which means that you don't need to create a lock, acquire the lock, and then release it. Everything is done under the hood by OpenMP. This pragma OMP4 is a compiler directive in OpenMP that tells the compiler that we want to parallelize a for loop. And this version is a shorthand version, because if you want to use this, you must have this directive before that. But here is a shortcut, the second one. Then you have this reduction, for example, that gives you a way to combine different data from different threads. So, and for the reduction, you have the operation, and you have the variable that you want to perform reduction on. We talk about reductions today and in the next lecture. And finally, you have a schedule. These are we talk about them. You have private variables and other things. So what I want to mention here is that you can have different compiler directives in OpenMP, and then by combining these compiler directives, you can have a high quality parallel code that works correctly as you might expect. And this is the this is OpenMP architecture, how it works internally. So it has a end user layer, which is the end user. Then you have the application written in OpenMP. Your application contains some library calls, some compiler directives, and some environment variables. Then it's up to OpenMP runtime library to manage your directives. I mean, to manage your program, like creating threads, managing them behind the scenes. And this runtime library uses operating system services for working with threads. So here is the place that you use, that OpenMP uses Pthreads like behind the scenes, and then those threads will be mapped into actual hardware threads. But you as a programmer work in this level that I'm highlighting. So you don't need to worry about these lower level things. But if you work with Pthreads, for example, you are working in this layer. Okay, so OpenMP is a little bit high level of writing parallel code. All right, so enough about introduction. So let's see some code. So here is a hello world program in OpenMP. So what you need to do is to include this header file omp.h, and then within my main file, I want to run this piece of code in parallel. So I don't create any thread and join and nothing. What I do is to tell the compiler using this pragma OMP parallel that I want this region to be executed in parallel, right? Then OpenMP checks how many threads you have available on your system. Then it creates a team of threads for you, and then each thread runs this specific code, right? So this part of your code here is called parallel region. And within this parallel region, you have different threads that execute the code in this parallel region. And for compilation on Mac and Linux, you can use this G++ compiler. So everything is similar to what we had before, but here you should add this flag with -f OpenMP, which tells the compiler this program contains OpenMP directives like this ones. Okay. This syntax works directly on Linux operating system, but for Mac users, you need to do a trick because Mac default compiler CLang does not support OpenMP. If you had problems, you can send me an email, but I can also put it on Moodle as well. And if you want to compile an OpenMP program using CMake, you can also use this configuration file that I provided here. Okay. So let's see what is the programming model in OpenMP, which is similar to the programming model with using the thread libraries that we talk about. And this programming model is called fork join parallelism, which is quite simple to understand. So as I mentioned, you have a master thread, or a main thread, right? Which is run. And then in some point, you are creating a number of threads, right? And then you assign a task to each thread. So in OpenMP, this region starts from here, the parallel region. And in Pthread and C++ thread library, when you create a thread, you are in this point, right? Then you create different threads, and main thread also is another one. So here we have a main thread and we have two other threads, right? So here we are forking. It is similar to fork, right? So here we are forking. We do our computation. So each thread handles a task, right? Task A, task B, and task C. And after they are done, they join to the main thread, which means your created thread now is destroyed. So, and you only have the main thread now. You continue execution, and at some point in your program, you have some other tasks that you want to perform in parallel. Then you create different threads again. You fork different threads, and then you join after they're done. And you fork again, and you're done, right? The good thing about this kind of parallelism is you can always start with a serial code, right? Like here, that is being executed only by the main thread or the master thread. And then you can gradually parallelize the parts that you think can be run in parallel. And OpenMP exactly allows you to do this in a very simple and efficient manner. Okay? So this is how fork join parallelism in OpenMP helps you to make your code parallel from a serialized version, and you can do it gradually. Okay. In OpenMP also, you can create threads, but you can request OpenMP a number of threads that you might need for your program using this this library call using this function, OMP set number of threads. For example, in this code, I am telling OpenMP that I need 4 threads for this parallel region that I have, but I will not necessarily get 4 threads because it depends on the OpenMP implementation, because everything is managed by OpenMP under the hood, even the number of threads. You can request the number of threads that you need, but it's up to the OpenMP to get you the number of threads that you want. So it really depends on the OpenMP implementation and also the compiler. So for example, here this code implements a parallel vector addition in OpenMP. As you can see, it's quite simple. Without this directive, it's a serial parallel vector addition. So you loop through these, you go through this for loop and you add these 2 arrays, but only by adding this directive, pragma OpenMP parallel 4, OpenMP will distribute the computations and the iterations of this for loop among a number of threads that it created for you by default or you requested. Then everything is done in parallel with very small change in your code, right? So that's how OpenMP simplifies things, especially when you have numerical calculations. Okay. And if you want to know how many threads OpenMP created for you and to check if it created the exact number that you needed, you can use this OMP get num threads within your parallel region. So it's important that you have this here, right? In this block that you have this pragma thing. All right. So now I can show you some examples, but we don't have time for today. So in the next lecture, I will show you this dot product example using Pthreads library, OpenMP, and also C++ standard thread library. And then we evaluate which one is simpler to write and how we can do parallel dot product using these libraries. And then we start another example which is numerical integration. And then we first write it serially and gradually make that program more efficient by using OpenMP and parallel implementation. Okay, so that's what I wanted to cover for today. So now you are aware of Pthreads, OpenMP, and C++ standard libraries. So you can play with them a little bit. I will also upload the code that I showed you today, so you can kind of change the code and see how it works on your own system. All right. So that's what I wanted to cover for today. So is there any question? All right. Okay,
So I have a
so
question.
yes.
What kind of IDE do you recommend that we use? Because
Sorry?
you mentioned lots of different commands to compile
Mm-hmm.
the code.
Mm-hmm.
So is it better if we work directly with the terminal, or what do you recommend for this course?
Yeah, I recommend you to use CMake that I introduced, but I didn't go through it, so I write it in the chat. So CMake is a build system for C++ and C applications, so it can automate the building process. But in the beginning, I would recommend you to work by the command line just to know how compilers work for these programs. But for your project and for your homework assignments, I recommend everybody to use CMake to automate the build system. Because when your program gets bigger and bigger and you have different source files, so it's not easy to compile everything using a command line interface of the operating system. Okay,
Okay, thanks.
you're welcome. All right, so have a nice week and see you next time. Bye.